If we roll a fair six-sided dice, what is the probability of us getting a 5? Well, it's not a trick question, it's 1 in 6, or about 16.7%. But what do these probabilities represent? Obviously, they're implying that if we roll this dice, we're going to have a 1 in 6 chance of getting a 5. But if we roll it 6 times, we're not guaranteed to get a 5 just once. In fact, we might get no 5s at all, or 6 5s in a row. So now you might ask, if our experimental results almost never line up exactly with our theoretical probabilities, how do we give meaning to probabilities in the real and random world? One way to approach this question is through frequentialism, which relies on the concept of long-term relative frequency. In our case, this means that as our number of dice rolls approaches infinity, our relative frequency, that is the proportion of 5s out of the total number of rolls, will approach around 16.7%. In contrast, Bayesian thinking interprets probability as an expression of a degree of certainty or uncertainty. So through a Bayesian interpretation of a dice roll, we would say that we are 16.7% certain we're going to roll a 5. This is a much less defined idea, as Bayesian statistics doesn't try to conform the random nature of probability to a more scientific and defined principle. The distinction between these two interpretations isn't too important to consider for a simple dice roll, but it has some huge implications when considering events that can't be repeated infinite times. This is important to remember when we're testing hypotheses through statistical inference. Hypotheses are ideas and so can't be repeated. They're either true or false. So relative frequency, and consequently the very concept of frequentist probability, loses its meaning. To combat this, frequentist inference procedures assume you repeat an experiment infinite times, which you don't, and then comparing to our generated data, calculate the probability of our observed data occurring. We artificially generate long-term relative frequency, which means that our conclusions rely on events we haven't observed. Due to the nature of Bayesian probability, however, conducting Bayesian inference doesn't require us to assume we repeated an experiment infinite times, so our conclusions are based on data we actually observed. Bayesian inference is all about taking our prior hypothesis and updating it with new data to formulate a new hypothesis. We compute what is called the Bayes factor, which compares the likelihoods of our prior and new hypothesis explaining for our experimental data. This is another advantage of Bayesian inference. We can directly compare the probabilities for our two hypotheses. Through Bayesian methods, we update our prior beliefs with new data as we discover it, becoming more confident in our ever-changing hypothesis. The Bayesian interpretation of probability has not been terribly popular in the past, mainly due to its intensive computational requirements. But breakthroughs have made this computation much easier, and Bayesian statistics has begun to see huge applications in machine learning, so it is continuing to gain in popularity. Bayesian thinking is unique in that it's all about updating your prior beliefs with new data, which is a critical component of both human logic and machine learning. So Bayesian inference may begin to overtake the frequentist style, or perhaps not. But either way, it wouldn't hurt if we all thought a little more like a Bayesian.